Hey guys, this is Uha from RV College of Engineering. In this video, we'll be discussing about metal organic framework based nanomaterials for electrocatalysis. The world energy demands have been rising at exponential rates in recent times. Among renewable energy storage and conversion systems, the catalytic conversion of energy has received tremendous attention due to abundant energy resources. Electrochemical systems are expected to produce green energy. However, under operating conditions, the performance is largely limited by high activation barriers, resulting in high overpotential, hindering both efficiency and conversion rate. Thus, electrocatalysts are always needed to enhance electrode performance by inducing low energy intermediates. Metal organic frameworks. Metal organic frameworks are a branch of crystalline porous materials with highly ordered permanent pore structures. MOFs are constructed by coordination bonds connecting metal-containing inorganic building blocks and polydentate organic ligands into three-dimensional interconnected networks, and their scaffolds remain rigid after removal of template agents. We can think of them as sponges with very tiny holes. The only difference is that sponges are not uniform. It is very hard to control the action of holes. In case of MOFs, we can make and manipulate the size of holes according to our desired criteria of separation and storage. Consider a fuel tank filled with methane. An ordinary fuel tank will contain very little fuel. If you were to look at the walls of the fuel tank containing methane, you would notice that the molecules are much less spread out. This suggests a simple improvement to our tank design. Firstly, simply extend the walls of the tank inward to increase the surface area. The freshly exposed surface will attract new methane molecules, which in turn will allow us to store more methane in our tank than before. A simpler and more effective idea is to simply fill our tank with sand. Each grain of sand adds a small amount of surface area, but millions of grains of sand can fill inside the tank. This will increase the internal surface area to a large extent and a significant increase in the amount of stored methane. Now consider MOF. Unlike sand, each crystal contains trillions of identical pores that allows methane to get inside. This manipulates the surface area available for methane storage. It also multiplies the surface area. This results in high-density energy storage using self-assembled materials. Material design for electrocatalysis. The performance of electrocatalysts has become the limiting factor in most of the promising electrochemical energy conversion systems. However, despite excellent catalytic activity, extensive commercialization of PT is largely hindered by high cost, which may account for more than half of the total price of a fuel cell stack, and poor stability. Criteria for energy conversion of electrocatalysts. Electrocatalysts can be divided into several categories, including precious metal catalysts, NPM catalysts, and metal-free catalysts. All of these classes have different challenges, and the electrocatalysts should be tailored accordingly. For an ideal electrocatalyst, all the important properties that limit the performance of an electrochemical system should be considered at the same time, including efficiency, exposed number of surface atoms, porosity, stability, robustness, durability, and cost. However, in most of the basic but important electrode processes concerning electrochemical energy conversion, catalysts meeting all these needs are yet to be found. So far, we have seen why MOFs can be used as electrocatalysts. Now let us see where they can be used and how they can be helpful. Oxygen reduction proceeds at the cathode of the fuel cell, where oxygen is reduced to water molecules as shown in the following half-cell reaction. The developed catalysts should have easy access of the oxygen species to the active species along with large exposure of the catalyst surface atoms. MOFs, as described earlier, provide an extremely high surface area framework with active metal centers. The high surface area ensures ease of access for the oxygen species, while active metal centers act as basis for catalysis reaction. Higher surface area and porosity with large number of active sites are considered as basic requirements of a good catalyst, but the development of catalysts based on traditional carbon supports consisting of micro, meso, and macropores could not fulfill the needs of high activity and mass transfer. The active sites for catalytic reaction are dominantly concentrated on the micropores of the catalyst and are mainly responsible for catalytic activity. However, macropores are needed for faster mass transport, especially at higher current rates. The mesopores can provide additional passages for electrolyte transport, but can result in additional tortuosity and mass transfer resistance. Additionally, mesopores have higher volume to surface area ratios in comparison to micropores, limiting the exposed active sites for catalysis. Hence, ideal catalysts are expected to have large number of active sites along with micro and macropores for enhanced activity and faster mass transport. This is an example. Now, let us consider oxygen evolution reaction. Generally, oxygen evolution reaction follows an electrochemical oxide-driven path in acidic electrolytes, but a hydroxide-driven path in alkaline electrolytes. There are many reactions which basically has four-step pathway for OER based on density functional theory. Calculations are shown below. It is generally agreed that change in free energy for each elementary step should be 1.3 volts for ideal catalysts. However, under real operating conditions, the binding energies of oxygen is much larger than ideal 1.23 volts. Moreover, in addition to higher free energies, the activity of OER catalysts is further hampered by irreversible adsorption of anionic species on the catalyst surface. Several fundamental issues must be addressed while designing efficient catalysts for oxygen evolution reaction. Hence, the ideal catalysts should have lesser free energy for elementary reactions, higher surface area, be highly hydrophilic, and corrosion resistant. Rational tailoring of MOF materials has been identified as an efficient method to derive highly efficient catalysts for OER. It was observed recently that delta G for OH can be decreased significantly by the introduction of additional functional groups on the organic ligands in MOFs. A zirconium-based ZrMOF was synthesized with amino and nitro functionalized 1,4 benzene dicarboxylate, and DFT calculations were used to calculate delta G for the elementary steps. It was further identified that addition of ammonia functional groups on BDC ligands could reduce the energy barrier significantly. Moreover, cobalt-based catalysts constitute important class of OER catalysts and have been investigated extensively due to their working capability under neutral pH, low cost, higher activity, and stability. Now let us consider the lithium-oxygen battery, the application of electrochemical energy storage to support the intermittent energy production systems and to realize the dream of electrification of road market is another challenge. Electrochemical activities of MOF-based materials on independent electrodes have been well studied as stated in the aforementioned parts. However, the ultimate purpose of electrode process research is the actualization of next-generation electrochemical storage systems to replace lithium-ion batteries For all-electric transportation, thus, inspection of the performance of assembled batteries is indispensable. Reverse lithium-oxygen batteries are an ideal form of such pursuance with a theoretical specific energy of about 10 times higher than that of the present commercial lithium-ion batteries. Carbon dioxide reduction. Carbon dioxide is the major component of fossil fuel combustion as well as the major greenhouse gas in the atmosphere. One of the major objectives of energy and environmental science is the construction of a carbon-neutral energy utilization system, which requires a sufficient way of recycling the waste carbon dioxide. MOFs have been widely used for carbon dioxide absorption, separation, and storage in the past decades, and recently their potentials as highly selective catalysts for carbon dioxide electroreduction were also explored. Copper is the only one with considerable production of hydrocarbons while still retaining a relatively high overall carbon reduction efficiency, and copper-based electrodes were widely researched particularly. Carbon-based MOFs have thus become the entry point for MOF-based carbon dioxide reduction. Besides copper-based catalysts, another well-known family of catalysts for carbon dioxide reduction is the homogeneous metalloporphyrin, which mimics that of chlorophyll in plants by the so-called artificial photosynthesis process under the assistance of light or electricity. Commercialization of MOFs. So far, we have seen the applications, merits, and limitations of MOFs in many different electrocatalytic reactions. Aside from catalytic properties and material designs, more important issues arise concerning the industrialization and commercialization of MOF-based electrocatalysts. For practical applications, the cost and yield of catalysts must be considered as major factors. Currently, industrial applications of MOFs are mainly converging on several fields including transportation, oleochemical industry, textile industry, respiratory systems, food packaging. Big companies have developed their own prototype, all-electric automobiles using MOFs as either adsorption enhancers in gas tanks or electrode additives in batteries. Thank you.